is our first streaming class. So I'll be trying this out in the classroom first, and then see if it works well, or maybe go back to my office for live streaming as well. But we're gonna try it out today. So before we continue our discussion on current mirrors, I would like to make some announcement regarding we have actually a quiz scheduled next week. So we'll be handling this online. So you make sure that you're registered on e-class, and then you should be able to do this online quiz next Thursday. And it will cover the range of Chapter 9. And we're still talking about how long the quiz will take, maybe 20 to 30 minutes. Depends on how long I will have to discuss with Professor Huang to make the final decision, but it will still be scheduled within the half hour at the end of class next Thursday next week. So we'll be online, again, online on e-class. Just make sure that you're registered, and then you'll be able to access all the exams. And it will be 10 single choice questions, okay? And covering Chapter 9, meaning Cascode amplifier and Cascode structures and current mirrors. So today, the plan is that probably I'm going to spend an hour on current mirror. So we're going to spend a little time, an hour on current mirror, and then the next hour I'm going to start the discussion on Chapter 10, which is differential pair. Okay? So on current mirror, basically, we still have a few examples or a few topologies or structures to cover. One is we're going to talk a little bit on cascode current source or cascode current mirror. So in order to provide cascode current source, you need to construct a cascode current mirror. So we're going to talk about how does one achieve that in terms of stacking up cascode structures in current mirrors, in realizing current mirror. And then we're going to talk about, last week, we mainly focused on N-channel or NPN-based current mirror. We're going to also talk about PNP and how does it apply to actual circuits. So we're going to apply this more to the single stage amplifiers. So we're going to go through a few examples to let you know how this analysis, what type of analysis you need to be able to complete, and what are the exercises you need to go through. And then we're going to go through a few examples as well. So let's first address how does one complete. Remember, we have cascode current sources. So if I'm using this is how one complete a cascode current source. So this is a cascode current source if I have a fixed bias. So what if I wanted to mirror it from another current source and providing a cascode, providing a fixed current which is designed by by reference. So to complete, this is a cascode current source. So if you want to do cascode current mirror, meaning that the current is being set rather than being set by voltage, we want it to be set by reference current. So the main difference is that it's still a cascode structure, but its current is set by a reference current source. So the basic structure is fairly simple. If you want to construct a cascode current mirror, it will look something more like this. If I'm doing the MOS version, then this will be the reference source, and then it will be the mirror through this diode connected structure as well. So I'm merely stacking two current mirrors. on top of each other. So this is how one complete a cascode current mirror. As I said, as we already discussed previously, the main purpose of having a cascode structure, let me label it first. So I have two pairs, M1, M2, M3, M4. So I have four, you should say two pairs stack on each other. So what is the main benefit of having a cascode current source? Or this is just to provide a current source, but it's the current. So the main idea is that the current I/O, let's say if I have identical transistors, so M1 to M4 are identical, then what it means is that I will then have the copying fast. So mirror simply means that I/O will then be equal to I reference. So this is how I set my bias level of the cascode current source. So this is the first. The mirroring is to set your level rather than using a voltage relationship. So if you look at the comparison between the two, if I'm using simply a biasing voltage to determine this, then my current I/O, let's say I/O. Without the mirror, my I/O will then be determined by mostly mu n Cox W over L VB1, VB2 minus VTH squared. So it will be transistors current characteristic determine my output current. So this voltage, this current is determined by your biasing condition, DC biasing condition. However, on the right, this current mirror will then allow us to set my current to the reference level. Therefore, I could have more flexibility in setting my reference, flexibility in setting the operating point, or I should say IDQ for the biasing circuit. And the other benefit, of course, first of all, you set it to the target level with more precisions and more robust toward environmental changes. The second feature is, of course, its output resistance R out will then be GM4 RO4 times RO2. So it's looking down from here, the output resistance from here is based on the gain of this transistor and RO2. So I would then have a high, so the feature is high output resistance. I could both obtain a precisely set operating current, and then I could, or biasing current, precisely, so precision in bias current. So this results in precision in biasing current. The other is then it results high output resistance. These are both desirable characteristic of biasing a circuit. You want to have a more ideal current source by having a high output resistance. The other is then increase the precision of the biasing circuit through this cascode structure. So these two are the pros. Of course, there's disadvantage of this type of design. So these are the pros. I should say pros. Let's look at the cons, meaning that what are the drawbacks of having this type of structures? So this is a classic problem with cascode, as we already discussed. The main problem with cascoding this structure is that we would then have a limitation on the margin, the movement, or output swing mostly. So your output voltage, your VO minimum, based on this analysis, VO minimum will be much more limited. It will be limited rather than by 2 VOV. If you look at this case on the left, you will see that if I have an overdrive, VOV, and there's another overdrive. If I could have freedom to determine my VB1 and VB2, in this case, the VO minimum for the case on the left will be 2 overdrives. We have already discussed this. This is the minimum level. It's actually can be set by VB2, VB1. So you set your proper VB1 so that this is VOV, then this will be 2 VOV at this output terminal, this minimum level. But if you look at this particular circuit, then there's actually more problem. So let's take a look at the biasing condition. So if this is 0 volt at ground, so this voltage is actually, let's say if it has, all of the circuit has the same overdrive, all of the transistors experience the same overdrive, then this will be threshold plus an overdrive, because this is VGS. Okay? And this level, so this level, you would then stack another VGS. Therefore, this level, the potential at node, let me label it. So let's say this is X1, this is X2. Okay? So potential at X1, let's highlight. Potential at X1, Vx1 equals to threshold plus VOV. If you go to the second floor, then it will be double of that, 2 threshold plus VOV. Therefore, because you're forcing this X2 to a higher level, therefore, my VO minimum is actually set by this voltage. Remember, this is the same as VB2. So VO minimum is Vx2 minus a threshold. Therefore, you get the final results will be 1 threshold plus 2 VOV. Okay? So the results is that if you're looking at the circuit on the left, because I have freedom to set my VB1, therefore my VOV will then be set, can be lower. My VO minimum will be lower in the case on the left. But for the Cascode amplifier, you can see that its VOV is actually 1 threshold higher. So if I give you an arbitrary number, let's say, let me use the left. Let's say if a threshold voltage of 0.5 volt is typical, and your overdrive of a design is typically maybe 0.3 volt. So on the Cascode amplifier, on the Cascode amp, your VO minimum, based on the calculation, should be 0.5 plus 2 times 0.2. This would then give me 1.1 volt. Okay, so you're 1.1 volt above ground, meaning that if my VDD, let's say if my VDD is 1.8 volt, and then you would then have very little margin to move. Remember, your minimum, your 1.1 volt above ground. Therefore, the margin of movement will be very limited. This will significantly limit upper swing. When VDD is low. So when your supply voltage is, as we already discussed, if your supply voltage is below 2.5 volt, you basically have very little margin, especially when you do Cascode structures. It will be even worse because of this limitation on your bias voltage on Vx2. So this will be 1 threshold worse. And 1 threshold is 0.5 volt. That's significant margin in a lot of the analog circuit design, especially under low supply voltage circuits. Okay, so this is on Cascode structure. Next, we're going to move on to examples on PNP or PMOS examples, mirrors. So let's look at a PNP examples. Typically, what we want to, for mostly amplification purposes, you probably wanted to have your amplifying transistor, meaning the ones that modulate current, meaning the transconductance, provide the transconductance of this modulation, depends on NMOS. Therefore, PMOS is probably best to use as the load. So let's look at a PNP curve mirror. So let's say if I have a So there's actually 3 transistors. Let me just label it Q1, Q2, Q3. So as I said, in order to bias my common emitter stage, Q3, this is the common emitter stage. So this is identical to a common emitter stage with a current source load. VCC. Okay? So this is equivalent to that. So if I want to analyze the common emitter amplifier based on this characteristic, the first thing I need to know is the reference current level. Let's say I have a ratio 1/n. So let's do some analysis as to how does one analyze this common emitter amplifier. So this is my input. This is the output terminal. So for a common emitter amplifier, to analyze a Q3, to analyze the circuit, one of the first things we need to know is its biasing current. So its biasing current, let's just give some numbers. Let's say I reference equals to 0.5 milliamp. My N equals to ratio between the 2 transistors, N equals to 2. So if that's the case, that would simply imply that this I1 should equals to about 2. Let's ignore beta effect. There will be 2I reference. There will be 1 milliamp. So based on this, we should be able to get GM3, sorry. GM3 is I1 versus VT. And then we should be able to find out the overall gain of this common emitter stage with PMOS current mirror load. The overall gain, voltage gain, should be able to, one should be able to determine its voltage gain. Voltage gain should be minus GM3 RO3 in parallel RO2. Okay? So how does one find out RO3? RO3 is early voltage divided by I1. RO2 is also early voltage of NPN, PNP. So once these device parameters, for example, early voltage and I should say I1, I only have one biasing current. Right. I1 is equals to IC1 equals to IC2. This is by ignoring base current effect. So once we have these parameters, we should be able to get our final results. Okay? So if, I'm just going to give some simple number. Let's say if VA1, VAN equals to VAP equals to VA. So let's say it both has the same early voltage. Therefore, this implies that because they share the same branch of current, therefore RO1 equals to RO2 equals to VA I1. So let's simply insert this. This will be GM3, RO in parallel. That will give me 1/2 GM3 RO. I'm simply going to insert a number, so this will be minus 1/2 VA over VT. Remember, this is the intrinsic gain of a bipolar technology. This is determined by technology. So it will be independent of gain, meaning that if I give you a question, well, the voltage gain depends on biasing current, or, for example, it depends on N or depends on I reference. It should be independent based on this analysis. This will be depending only on intrinsic gain. Okay? So this is a PNP example. Let's look at a more complicated mirroring system. So other things you need to be able to analyze or find out in terms of biasing design is this type of question. For example, if I'm having a reference source, it's actually a NPN current mirror. So this is a circuit example. Let me spend a little time to draw it. Instead of having a PMOS, if I have a source which comes from above, I reference, then this will then experience two mirroring effect. I will first mirror by let me label it first. So this is, let's say, starting from the left, Q1, Q2, Q3, Q4, Q5. So if I'm going to label where the input signal is coming in, and this is where the output signals go out. So if you look at this particular circuit, as I said, if I give you this type of circuit in the exams, you should be able to identify the role of each one of the transistors. So let's say, and also you should be able to determine the biasing current at each branch. So let's say if I give you for example, this is, I'm starting with 1 milliamp. And each pair, so I have two pairs. I have Q2, Q1 as one pair. So Q1, Q2 is a NPN current mirror. Q3, Q4 is the PNP current mirror. So you should be able to first identify what are these what are these transistors or circuits are meant for mirroring the current down to biasing the final, the actual amplifying stage. So Q5, this will then be my common emitter stage for gain. So to analyze this type of circuit, one of the things, as I said, we know that the overall behavior of the circuit will depend on its biasing current. So one of the key important things is to find out the current at each branch. So I know this would determine IC1, IC2, and IC5. So first order analysis, you could simply ignore base current effect. So if we ignore first base current effect, you should be able to find out that IC1, let me give a ratio. So if this is 1/5, and this is 2/1, I just give a ratio, different ratio on transistor sizes. So based on this, I know that IC2 over IC1 should be approximately, ignore base current. So that would be a ratio of 5. So first I know that IC2 will be 5 milliamp. And then if you base on this current mirror, tell us that the collector current IC4 versus IC3, this current mirror tell us that the current ratio should be 1/2. But because 2:1, this is larger, this is smaller, so you're scaling down. Therefore, and we know that IC3 is approximately equals to IC2 because they're same branch. There's a slight base current effect. If you need to include it, you could simply just do KCL to include the beta effect. But if not, just to get a ballpark as to the current level, then this will simply be, so we should be able to get IC4 equals to 1/2 IC2, and this is 2.5 milliamp. So I'm doing this exercise just to let you know that you should be able to identify all the current levels at each branch. So I should be able to know that my biasing at Q5 will be set by this multiple mirroring system. Okay? And finally, we're going to go through maybe 2 or 3 examples on how does one analyze this type of mirroring circuits. So I can do this type of mirroring circuit allow us to bias single stage amplifier, which we have already introduced in previous chapters. So let's go through an example. On an emitter follower circuit. Emitter follower circuit design. So the basic spec, let me limit the spec. Typically, in a design problem, you'll be limited by mostly power. And then because it's a follower circuit, so the design target is this output resistance. You want it to be lower than 50 ohm. And then we're going to assume the device parameters, early voltage, ignore early voltage, infinite, beta equals to 100. Okay? So this is how you bias a emitter follower. So let's say I have an ideal current source, a reference current source, and then it's being fed into a current mirror, NPN current mirror. And this current is then mirrored over to become a sinking current source. And this sinking current source is then used to bias. Sorry, let me see. This is VCC, 2.5. So this is being used to bias this follower circuit. So this one is actually my follower circuit, Q2. Let me just use Q3. I want my pair to be 1 and 2. Okay, so my current mirror pairs are 1 and 2. And then this follower circuit is Q3, construct by Q3. So because this is a emitter follower circuit, this is the input terminal. This is the output terminal. So basically, the requirement is on the right, which is that it needs to dissipate a power less than 3 milliwatts and then provide an output resistance of 50 ohm. So first of all, in this type of question, we wanted to first to make sure that our output resistance will meet the target. So if we look at this circuit, we know that its output resistance depends on, let me get my color. So if you're looking in, your output resistance is basically looking up and looking down. For looking down, this will be RO2, because this is a current source. So you're crossing collector emitter, so that's RO2. If you're looking down from the emitter, this is 1 over GM3. Okay? So the overall R out in this case, first of all, let's define our R out. In this case, will be 1 over GM3. That's our main follower circuit, follower transistor, in parallel with the loading resistor. And we know that 1 over GM is typically designed to be much, much larger than RO1. So this is approximately 1 over GM3. And we know that GM is equals to IC3 VT. So this is VT IC3. So this would then set my IC3. This is 50 ohm. Because this 50 ohm would then tell us that your biasing current needs to be as large as what? To make sure that it reached 50 ohm. So that's just set our IC3 to 0.25 milliamp. So this is how we meet the spec. We need to set the current to at least 0.5 milliamp in order to meet the spec of delivering output resistance of 50 ohm. Okay? And then the other part is more like a design problem. So this is the key. It will meet our target spec. And then the other is that you minimize your overall power dissipation. So the power of dissipation will then be VCC times the overall current. So that will be IC3 plus I reference. Okay? So we know that this needs to be smaller than, you just want to make sure it does not exceed 3 milliwatts, the maximum power. That is to say that IC1 plus I reference needs to be smaller than 1.3 milliamp. Therefore, your reference current level needs to be smaller than 0.6968. Okay? So you can either set it to be a smaller current level or just make it identical. So in this case, if we make it identical, it will still fit our target. So the design will then be to set Q1, Q2 identical. That means that my I reference level will then be the same as IC1. Okay? Of course, you could correct it with the beta effect. So your I reference is actually, if you want to correct it, let me be more precise. So I reference will actually equals to 1 plus 2 base current times IC2. So it'll be slightly higher, but just 2% increase. So it will still be lower than 0.68. Okay, so you can set it identical so it will meet the target of delivering the level. So this would then set. So the other thing is that you set I reference to be 1.02 times, I don't know what the value is, but this will be approximately, is that correct? You can double check. So the thing is that I'm setting two things. That the whole design, you need to determine your I reference level. I don't know, 2%. And then the ratio. So these are the two design results. You set the current level and set the transistor size. Of course, this is not the only answer. You could actually make it 1/2, and this can be smaller or a different ratio design, as long as it meets the design target. Okay, good. So we're going to also go through an example of a common source amplifier. So I'm going to go through an example of so example 2. We're going to talk about a common source amplifier stage with also PMOS, with PMOS current mirrors. So let's say I have a low supply voltage system, which then include a PMOS current mirror. So first of all, I set my PMOS current mirror and M1, M2. And it would then be, the reference current source will be feed to the PMOS current mirror. And this can be used to bias my active amplifying stage. So the yellow part is my M3, which is the common source amplifier. As I highlighted on the left, this will be identical to this will be equivalent to a common source amplifier input-output, where you're biasing with a current source, which the current source is being constructed by this current mirror circuit. So this will be my input terminal, and this will be the output terminal. So for this example, there's also a design problem. Therefore, it does not have the same answer. You can design on your own. But let's just give the design target. The target is that it will provide a voltage gain, a magnitude. We know that it's an inverting amplifier of 20. And then I know that device size of transistor 3 is fixed at this particular size. And device parameters, is going to give device parameters. So lambda n equals to 0.1, lambda p equals to 0.2, And then I have mu and Cox. Because there's the MP, 100 microamp volt square, mu P Cox equals to 50, half of that. So to reach this target with a setting of M3 already chosen, the size of M3 already chosen, we want to make sure that you find the ratio W over L to design your current mirror. Okay? To find this proper sizing of your transistors, W over L1, the current mirrors, and your reference current level in order to reach the target. So anyway, you start with the target as well, because remember in the previous emitter follower circuit, you start with the spec, which is the output resistance. In this case, our spec is overall gain. So the gain, we know that VL versus Vin equals to 20. It's actually GM3 times RO1 in parallel RO2. Okay? And this is a little bit tricky because we actually do not know the biasing current yet. So you have to determine the current with the constraint. So we're going to express everything with the current. So we know that the GM can be represented as VOV. And then this will be lambda ID in parallel lambda P ID. So remember, we need to determine its biasing current ID3. So let me be precise. It's ID3. So we already know our lambda P. Okay? So we only know lambda I. I forgot to do another constraint. So this target is to provide a gain of 20 with, I forgot one other spec, sorry. Let me write it down. The target is provide a gain and then output swing has to be larger than 1. Okay? So if output swing is larger than 1, it will then cast a constraint on our overdrive. So let's say if I'm having an output swing of larger than 1, which is output swing. Your output swing, I should say, VL max minus VL min. It should be determined by VDD. You have a overdrive on top, so that's minus VOV2 minus VOV3. So this needs to be larger than 1 volt. That is to say, VOV1, 2 plus VOV3 should be smaller than 0.8 volt. Right? Because my supply voltage is only 1.8 volt. Okay? So in order to do this, we need to set your VOV. So if we set, this is determined by the design. So you can set it to whatever level you want. So if we set VOV to be 1/3, I should say 0.33 volt. This is just a setting. So you can set your own level. Then put it back into this equation. We should be able to get our current level. So the current level will then be 0.6 milliamp. Okay? So once we know this current level, we can then set the ratio. You can set so that both have the same VOV. So you can set VOV2 equals, both have the same overdrive so that you have the same swing center at the middle. Therefore, whatever the distance between top to the ceiling and bottom to the ground is the same. So once this is being set, we could then set it up. We can then determine our size. Therefore, the same current but different. Oh, I don't have enough space. Let me get my space. You can do the exercise on your own. I'm not going to go through the detail, but just to give you the answer. Yeah, I shouldn't get rid of it. Okay, let's take a break for taking the pictures, and then we'll come back. Otherwise, let's take a break. And we'll come back in 10 minutes. Let me write this back. 等我一下。我们先休息，你们先。OK， 真的吗？还有吗？可以哈。Okay, so let me finish the discussion on the example 2 on the PMOS. So once we set our overdrive levels so that I know that my VO max will then be 1.8 minus 0.33. This will give me 1.74. VO minimum will then be 0.33. This will be the same as VOV3, right? This is VOV2. Okay? So then, because we already know that it has the same overdrive, so we could determine the size. We know that ID is 0.6 milliamp. This is set by gain, the target gain. So we know that if this is 0.6, this actually equals to ID2. So this would then give me 1/2 mu p Cx W over L2. VOV2. Okay, so in this equation, I already know this level. I already know this is 0.33. So I could determine W over L2. So W over L2 is found out to be, based on this, because your device is, mu and Cox is twice as small, but the same current. That is, you can actually obtain that WL2 is 2 times WL3 to get the same current, because it's PMOS. So that is 0.1840. Okay? So for the current mirror side, then it can be arbitrarily determined. So the easiest way is to set M1, M2 identical. It can be either identical or not. So then so this, if it's an identical, then I reference equals to ID3, ID2 equals to 0.6 million. Okay? So this is arbitrary. You can determine, you can set it various ways. So there's 2 settings, meaning that it's determined by designer. You can set them identical or not. If it's not, then you could do the ratio yourself. The other thing is that we set our VOV just to make sure that it was still within the boundary of providing a swing of above 1 volt. Okay?